Hey everyone, in this video we're going to learn about forces and get an introduction to free body diagrams. Everything that we've learned so far fits into the category of kinematics, which covers how objects move, or how to describe the motion of objects. We used kinematic equations to help us describe the position, velocity, and acceleration of an object, so we could answer questions like how fast is the object moving? Where will it be at a certain time? And how long will it take to travel some distance? But in every example, we were told how the object was moving. We never actually learned what was causing the object to move. Let's say we were given an example like this. A curling stone slides across ice with a constant velocity of 3 meters per second at an angle of 45 degrees. What is the x displacement after 2 seconds? We would take that velocity and use a kinematic equation to find the displacement. But why was it moving at a constant velocity? Why wouldn't it slow down over time? In projectile motion, we said that the vertical acceleration is always g, 9.8 meters per second squared downwards, and the horizontal acceleration is 0, so the horizontal velocity is constant. Then we could use the values that we were given and some kinematic equations to answer questions about the motion. But why is the horizontal velocity constant? And why do all objects accelerate downwards at 9.8 meters per second squared? That's what we're going to learn about in dynamics. Dynamics explains why objects move and what causes objects to move. And we'll learn about mass, forces, energy, momentum, some fundamental laws, and more. We're going to cover dynamics throughout the rest of the course, starting with this video. Alright, so why do objects move in different ways? Things are moving and not moving all around us, but we probably don't think about why. If you're trying to move a box and you push it as hard as you can, but you can't get it to move, why doesn't the box move? If you grab a book and slide it across a table, why does the book eventually stop moving? If a hockey player passes a puck across the ice, why does the puck keep moving at a constant speed? If you're trying to move another box, and you are able to slide it across the floor, why does this box move? And why would it move at a constant speed if you're pushing on it? And if we drop a ball from some height, why does the ball accelerate downwards? Why doesn't the ball move at a constant speed? These scenarios might not seem that interesting, but almost everything in the world and everything in the universe behaves the same way as one of these 5 examples. It either doesn't move, it slows down, it moves with a constant speed for different reasons, or it speeds up. It could also change direction, but we'll get to that later. In the next few videos, we'll learn why these objects move in different ways using Newton's 3 laws of motion. But before we can understand these laws, we need to learn about forces. So what is a force? How do we draw one? And what are the different types of forces? A force is really simple. It's just a push or a pull. Let's say the person on the left is pushing on a box, and the person on the right is pulling on a box. In both cases, the person is applying a force to the box. Or we might say the person is exerting a force on the box. These mean the same thing. Forces always come from the interaction between 2 objects. A force acts on one object and is caused by a different object. In this case, the force is acting on the box, and the force is caused by the person. So the 2 objects are the box and the person. Even though people are pretty sophisticated objects, and we can do a lot of things and move in complex ways, we're still just objects when it comes to physics. If a person applies a force to an object, we don't need to think about what the person is trying to do or anything complicated like that. We just treat it like any other force. For example, if we attached a large spring to the box and we squeezed it against a wall so that the spring wants to get longer, the spring would push on the box just like a person would push on the box. This force is acting on the box, but now the force is caused by the spring. Or if we stretch the spring so it wants to get shorter, the spring would actually pull on the box, just like a person would pull on the box. We'll cover spring forces in another lesson, but the point is, objects exert forces on other objects, and a force is just a push or a pull. But what does a force look like? Well, we can't actually see a force, but sometimes we can see the effect of a force. If this person exerts a force on the box, and the box moves, we can tell that the motion is probably caused by the pushing force from the person. Or if we exert a pulling force on a spring, or something like a rubber band, we can see the spring gets longer because of that force. But most of the time, we won't be able to see the effects of a force, at least not every force. For example, this book is sitting on an inclined table. Even though the book isn't moving, and nothing seems to be stretching, there's actually 3 forces that are acting on the book. So even though we can't see a force, we can draw a force. A force is a vector. It has a magnitude and a direction, and we represent a force with an arrow and a label. The arrow points in the direction of the force, and the length of the arrow represents the magnitude or the strength of the force. This is just like when we drew displacement, velocity, and acceleration vectors. So now, we might say the person is exerting a force F on the box. F is just the default variable or label that we give a force. We could also add a subscript, like the force exerted by the person on the box. The person is pushing the box to the right, so the force vector points to the right. For translational dynamics, we can draw the force vector anywhere as long as we know what the force is acting on and what's causing it. We could draw the force like this, we could draw it like this, or we could draw it somewhere else. But as we'll see later when we talk about free body diagrams, we usually draw a force vector so it starts on the edge of the object that the force is acting on, and then it points in the direction of the force. This way, the force doesn't overlap with the object, and it's easier to see. But the most important part is the direction of the force. So that's how we draw a force, but how do we describe the strength or magnitude of a force? How much force is this person exerting on the box? We measure a force using the SI unit of newtons, abbreviated as capital N, and named after Isaac Newton, the guy that described motion using these 3 laws. So let's say this person is pushing on the box with a force of 10 newtons. That's the magnitude or strength of the force. A newton is actually a derived SI unit, and 1 newton is equal to 1 kilogram meter per second squared, which will make a lot of sense when we cover Newton's second law. Also, 1 newton is roughly equal to 0.22 pounds. A pound is actually a unit of force, so we could say this person is pushing on the box with about 2.2 pounds of force. And remember, the length of the vector represents the magnitude of the force. So if the person pushed twice as hard with 20 newtons of force, the force vector would be twice as long. And the vector points in the direction of the force. So if the person was pushing the box to the left, we would draw the force vector pointing to the left. And what if the person was pulling on the box? If they're pulling to the left, then the force vector points to the left. And if they're pulling to the right, the force vector points to the right. It doesn't matter if a force is a push or a pull, the vector always points in the direction of the force. There can also be multiple forces acting on an object at the same time, and there usually is. Here we can see 2 people are pulling on the box in different directions. Once we start to deal with multiple forces, we may want to give them subscripts, and we could label these forces as F1 and F2. So that's an introduction to forces. Let's take a look at the forces that we'll learn about in this course. So we just looked at a person pushing or pulling on an object. This is what we might call an applied force. This isn't really a type of force, but a problem might just tell us that a force is applied to an object without telling us what's causing the force. We might label the force with something like F push or F pull. The problem might use another variable, like P, or we might just be given the magnitude of the force, like 10 newtons. One of the first types of forces that we'll learn about is a normal force, which we'll label as Fn. A normal force exists between any two objects that are in contact with each other, so it shows up all the time. It's called a normal force because normal means perpendicular, and this force always acts perpendicular to the surface, no matter which way it's oriented. So this table is exerting a normal force on this book, and the ground is exerting a normal force on this ball. Another very common force is a friction force. This is usually labeled with a lowercase f, but you could also label it like this. A friction force can exist between any two objects that are in contact, and it always opposes motion. So this book isn't sliding down because the table is exerting a friction force in the other direction. Friction forces are everywhere, and they're the reason that moving objects eventually slow down and stop. But friction also allows you to walk and drive a car, and it prevents everything from sliding around. Another force that we'll learn about is a tension force, usually labeled as T, but you could also use Ft. Tension is a pulling force that we'll see with things like ropes, strings, and cables. If this box is being pulled by a rope, we're going to call that pulling force a tension force. We can also change the direction of a tension force without changing its magnitude by using a pulley, and we'll learn more about pulley systems later on. And like we mentioned before, a spring can exert a spring force on an object, which we can label as FSP for spring. It takes some force to stretch and compress a spring, and the spring will exert a force on the objects that it's attached to. A lot of things that we use, like pens, work by using springs, because we can move stuff in a specific way by applying a force. Another very important force is a gravitational force, which we're going to label as Fg. In classical mechanics, which is what we're learning in this course, what we experience as gravity is the Earth pulling down on every object with a gravitational force. This force exists between any two objects with mass, and the gravitational force that exists between the Earth and this ball is the same gravitational force that exists between the Earth and the Moon, and it's what keeps the planets in orbit around the Sun. There's two more forces that we're not going to learn about in this course, but we should definitely mention them: a magnetic force and an electric force. A magnetic force is what causes two magnets to be attracted or repelled away from each other. It's what causes a magnet to stick to your fridge, and what allows us to use a compass to navigate using the Earth's magnetic field. An electric force is what causes charged particles to be attracted or repelled. Everything that uses electricity only works because of the electric forces between the electrons moving around in the wires. You might have noticed that the forces on the left exist between two objects that are touching each other, and the forces on the right exist even though the two objects are some distance apart. We call the forces on the left contact forces, and the ones on the right non-contact forces. The Earth exerts a pulling force on an object even if it's far away. Magnets attract and repel each other at a distance, and so do charged particles. It might seem weird that an object can push or pull another object that it's not touching, and it is weird. It took a long time for us to figure out that this is how things work, so don't worry if it's not intuitive at first. We'll learn a lot more about gravity in another lesson. So these are the different types of forces that we're going to be learning about. Even though they're different, they're all forces, and they all use the same unit of newtons. They have different causes, and we use different equations to calculate them, but when we're using Newton's laws of motion, all of these forces are basically equivalent. Every force is just a push or a pull. But you can see how things might get complicated when there's a lot of forces acting on an object. To keep things organized and help us see what's going on, we use free body diagrams, also known as force diagrams. A free body diagram, or a force diagram, is just a picture that shows a single object, a body, and all of the forces that are acting on that object. So here's a picture of a person pulling on a box with a rope. The picture includes the box, the rope, the person, and the ground. But the free body diagram of the box looks like this. It only shows the box and the forces that are acting on the box. In this example, there's a tension force from the rope, a friction force from the ground, a normal force from the ground, and a gravitational force from the earth. Like we said before, we can draw these forces anywhere in the diagram as long as they point in the right direction. But we usually draw a force starting on the edge of the object and pointing in the direction of the force. For a free body diagram, we only include a single object, and we do not draw any other objects or surfaces, which is why we call it a free body diagram. The body, which is the box, is free and it's isolated from the environment and other objects. Also, we only include the forces that are acting on this object. We do not include the forces that this object is exerting on other objects. Also, we can either draw the object, or we can represent the object with a dot. This might make things easier to see if the object is large or has some weird shape. So that's a quick introduction to free body diagrams, and we'll learn more about how to use them in the video on Newton's second law of motion. But they're basically just a way to focus on one object at a time and see all of the forces that are acting on that object. Whenever we work on a physics problem for the rest of the course, we always want to start by drawing a free body diagram. As we learn more about different types of forces and Newton's laws of motion, you might start seeing the forces that are acting on the stuff around you. Even if something isn't moving, there's probably some forces that are causing it not to move. And when things do move, there might be more forces involved than you think. Some free body diagrams will be pretty simple, and some will be a little more interesting. And even though we can't see them, we'll know what forces are acting on the stuff around us, and we'll know why things happen. In the next video, we'll learn about net forces, Newton's first law of motion, and we'll come up with explanations for the 5 scenarios that we saw earlier. But that's it for this video, so let's do a quick summary. Kinematics is the study of how objects move and how to describe motion. Dynamics is the study of why objects move and what causes them to move. We're going to use Newton's laws of motion to explain why objects move and why they don't move, and we need to understand forces in order to understand Newton's laws. A force is just a push or a pull. It acts on one object and is caused by a different object. We can't see a force, but sometimes we can see the effects of a force, like when an object moves or stretches like a spring. A force is a vector. It has a magnitude and a direction, and we represent a force with an arrow and a label. The arrow points in the direction of the force, and the length of the arrow represents the magnitude or the strength of the force. The SI unit for force is a Newton, capital N, which is equal to 1 kilogram meter per second squared. And there can be multiple forces acting on an object at the same time, in which case we might want to give them subscripts, like F1 and F2, so that we know which force we're talking about. There are many different types of forces, and these are the forces that we'll be learning about. There are other important forces, like magnetic and electric forces, but we won't cover those in this course. Forces that occur when there's physical contact between two objects are called contact forces, and forces between two objects that are some distance apart are called non-contact forces. But all of these are forces, they're just a push or a pull on an object. They all use the SI unit of newtons, and we're going to use all of them with Newton's laws of motion in the same way. A free body diagram, or a force diagram, is just a picture that shows a single object, a body, and all of the forces that are acting on that object. We only include a single object, the box, and we do not draw any other objects or surfaces. Also, we only include the forces that are acting on the box. We do not include the forces that the box is exerting on other objects. Drawing a free body diagram will always be the first step in solving physics problems for the rest of the course. And even though forces are invisible, hopefully you'll start to see all of the forces that are acting on the stuff around you as we learn more about different types of forces and Newton's laws of motion. Alright, that's it for this video. Thanks for watching, and I'll see you in the next one.